You are recording. Good. We go here. All right. Last time, what did we do? We talked about the binary eutectic system. Talked about binary eutectic system, but the system was last time we talked about the copper silver system. The components of the system were the copper and system. We have the same phase diagram. The eutectic again. We will look at another example of that, which is the lead tin system. So we have, instead of copper and silver, we have the lead and tin. Just to give you an idea that there are other systems as well. They will not behave exactly the same way, but the trend will be the same. The shape of the phase diagram, as you can see here, is basically the same. The shape of the phase diagram, it is the same as what we have covered previously. Look at this one here. This is the copper silver. Actually, the shape of the phase diagram is the same, except that the details are different. So we are having, for example, one important point, which is the eutectic point. It is this point. It is occurring at a different composition, of course. This is 61.9. Previously, we had different. The eutectic isotherm occurs at 183 degrees centigrade. There it was 779 degrees centigrade. But the general look is the same. This is a single phase. These are the liquidus lines in the same way. This here is the alpha solid, and that's a solid solution, and this is the beta solid solution. And here you have two solid solution phases coexisting together. So basically, you have the same condition there, except that the eutectic point and the details actually occur at different compositions and temperatures as well. So the alpha phase, a solid solution of 10 in lead. So this is the alpha. It's a solid solution of 10 in lead. The mother material is the lead actually. So the solvent is the lead, and the solute is the tin. Is Sn. On the other hand, the beta solid solution, it's a solid solution which is rich in tin. So there basically the solvent is tin, and the solute will be the lead here. So this is the only difference, and this is what we are saying. The eutectic invariant point occurs at 61.9% by weight 10, and of course the rest will be the lead, and it occurs at 183 degrees centigrade, which is that temperature. The eutectic isotherm, that line occurs at 183 degrees centigrade. One application to this phase diagram basically are the solder materials. Solder materials are materials which you use or commonly use in order to weld electronic circuits together. For example, you have whatever circuit, a resistor, a capacitor, a diode, whatever you want to connect in the motherboard, you normally use solder in order to weld the circuit parts together. So this solder material, lead is used. It is a good material to do the soldering there, but unfortunately lead has, if you see now what is the melting point temperature of pure lead, you can see it from the phase diagram. If you go from here, that's the pure lead actually, 100% lead, and that is 100% tin from here. So at 100% lead, where will it melt? Well, that's solid, that's solid, that's solid. Once you reach to this point, since that's a pure material, this is the behavior of pure material, they melt across a point, remember? Unlike when you have an alloy, except for the eutectic point, they melt across a range of temperature. So where does it melt? It melts something like 330 degrees centigrade. It melts there. It becomes a liquid. Now, that melting point temperature is high. But if you mix it, if you alloy it with tin, what is going to happen? As you add the tin to it, you see the melting point temperature the liquid across the liquidus line is reducing actually to a minimum of 183 degrees centigrade. So basically, the solder material used in electronics, normally they put 60% by weight tin and 40% by weight lead. Why is that? Which is nearly there, which is nearly very close to the eutectic point, which is at 61.9%. Okay, that is 61 is very close to that. So to reduce the melting point temperature actually, and what does that benefit? Well, it benefits us a lot actually, since we have millions and millions of electronics are soldered actually, are welded every day actually. I can say millions of them are done. If you reduce the melting point temperature, it reduces the energy which you need and to weld those materials for millions of connections or welds. You reduce the capacity of the machine that you want to use in order to do the welding, because you are reducing the melting point temperature drastically. So this is what is done. One of the applications, how would you reach to that? Actually, from the phase diagram, you can see this is the composition you want in order to reach the lowest melting point temperature for this alloy, basically. Another thing we want to look at also is that we start with practicing how can we, using the phase diagram now that we are acquainted well with the phase diagram, if we have the temperature and the composition of the alloy, then how can we answer those 4 questions? The 4 questions which we said are important. If we have the temperature and composition of the alloy, how many phases will be there? What the phases are? What is the composition of each phase? And what is the proportion, the weight fraction of each phase available at that condition? So we can just have a start point practice here. Let's say for a 40% by weight nickel, of course, I don't have to mention that because it's binary, but we are mentioning that also. 60% by weight lead. Obviously, if I don't give you this means that we have 40% by weight lead and 60% by weight, tin and 60% by weight lead. And if we were at 150 degrees centigrade, find the phases present, the compositions of each phase, the relative amounts of each phase in terms of mass fraction, so which is the proportion. So we will go to the phase diagram basically at 40% by weight tin and at 150 degrees centigrade. So that is basically, this is 20, 40, 60, so this is 40. And at 150 degrees centigrade, this is 100, that's 200, in between is 150. So you are basically here. How many phases do we have here? We have 2 phases. The phase diagram tells us in this area, all that area, we have 2 phases there. The alpha solid solution and the beta solid solution. So 2 phases, and what they are the alpha solid solution and the beta solid solution. What is the composition of each phase? What's the composition of alpha? What's the composition of beta? Well, what do we do in order to determine that? To determine that, we draw a tie line, a straight line like that, follow through like this. It intersects the Sylvus line here and there. So if we drop a vertical, basically coming down like this, I'm not very good at the mouse here, we have basically 10, about 10, okay? And if we go from here to there, so we have nearly, let's say I will take 98. I will say as if we have 98% by weight 10 there. So then, therefore, if we are intersecting with the alpha phase here, we are getting the composition of alpha, which is 10% by weight 10. Hello, Ayla. 10% by weight 10. Yani 10% by weight Sn. And if we want the composition of the beta, then we intersect with the Sylvus line at the beta phase, and we drop a vertical from there and read that number. It will be 98% by weight 10, of course, because the readings there are in terms of 10. So that's the composition. So we have two phases. What the phases are, they are the alpha solid solution and beta solid solution. What is their composition? These are their compositions. The alpha solid solution has 10% by weight 10, and the beta solid solution has 98% by weight 10. What is the proportion of each phase? We use the Lever's rule, and to use the Lever's rule, we say weight percentage of alpha, for example, if you wanted the alpha phase first. So we use the Lever's rule. What is the Lever's rule here? This is the alpha phase. So, and that is the line, that the segments of the line that we want to look at, the tie line. Two segments we have, that is S, which is from here to there, and we are going to refer to this as R, which will be from here to there, and we say that the Lever's rule says that it is the far dimension. This is the alpha. We want weight fraction of alpha. It is the far segment, which is S yani. So it will be S divided by the total there, S plus R. So you have R plus S. So this gives you what? Equals to, what is the S equal to? It's equal to 98 minus 40. So it's equal to 98 minus 40. All right, that's it. That is the value of S. It's 98 minus 40. This is the segment from here to there. Here we are reading 98, and here we are reading 40. So it's 98 minus 40 divided by S plus R, which means that this S plus this R. So we, instead of doing the S alone and R alone, we can just say the total will be from here to there, which is 98 minus 10, basically, which will be 98 minus 10, which is basically 88. If you calculate this, it will give you, as we have here, so that those are the ones that we had already. It will give you weight percentage of alpha will be 58 divided by 88, and of course you need to multiply here by 100 to get 66%. That is the weight fraction of alpha. In order to get the weight fraction of beta, you can do the same thing. You can do the same thing here. Weight fraction of beta equals to, and on the other hand, this is the beta. Now you want the far segment of the tie line, so it will be R, this R divided by R plus S. So it will be again here R divided by R plus S, and the R is equal to what? R is equal to 40 minus 10, which is equal to 30. Basically 40 minus 10 is equal to 30 divided by that total from here to there, which we already found here, 98 minus 10, which is 88 basically, and you multiply this by 100 and you get the weight fraction of beta. Here it is equal to 30 divided by 88 times 100. To get it in terms of percentage, it will become 34%. Obviously you could have gotten this, and instead of that you could just say weight fraction of beta is equal to, since it is percentage, we multiply by 100 is equal to weight 100 minus weight fraction of alpha. You say 100 minus 66, and this gives us 34, which is this answer basically, which we get in the same way. This is just to practice how we use the temperature and composition to locate ourselves on the phase diagram, and then determine those four things that we want to get, how many phases we have, what the phases are, what the composition of each phase, and what the volume fraction of each phase is as well. But as we go towards the end of this lecture, hopefully we will see that we cannot just do that. We need, this is just to practice, but in reality we need to do something else. We need to know how do we get to this point as we cool, which we relate to the history of heat treatment. We need to know the history of heat treatment in order to know, first of all, what microstructures we have, and then we go and apply this. We will see that in a minute and you will understand what I mean. So this is just to practice, but in reality, if we are cooling down, we would have different phases other than, a little bit different than the alpha and beta as well. We will see in that. Before we do that, we need to go into the development of the microstructure of the material. This is the eutectic phase diagram, just showing you another one so that you are acquainted with the different shapes there. So that is the same thing. Now let us look at the development of the phase diagram. Any questions, guys, so far?
دكتور
I need some. Yes.
في المسائل مال الفيز دايجرامز الفيزز نفسهم دائما يكونوا موجودين في الدايجرام، يعني الليكويد والالفا سوليوشن هاي.
مثل ما أنا in the same way I am giving it to you, that's the phase diagram. I'm not adding anything. This is how the phase diagram is given. This is given. This is given. But you need to know what they are. You need to know the point here is there. You need to know what this point is, right?
تمام دكتور.
All right. Then let us now look at, in the same way we dealt with when we dealt with here. So we did in this specific page, we saw how the microstructure development happened, this is what we said, development of the microstructure in the isomorphous alloy. So we went from here to the end and we saw what type of microstructure we produce. In this case, if you go from here to there, if you go from here to there, from here to there, from here to there, basically you would be making the same microstructure. But in the binary eutectic system, we will have a little bit different. And that's why if you are going from 0 to nearly 2, if you extend this down, it will be up to intersecting at nearly 2% by weight. So from here, from 0 to 2, basically certain microstructure is going to develop. From 2 to 18.3, another microstructure is going to develop. From 18.3 to 61.9, another microstructure is going to develop. At the eutectic point exactly, a specific microstructure is going to develop, and so on. Again, here is a mirror of what we have here, exchanging the alpha with the beta, so we have the same case there. And here also, if we are going down there, it's the same case as we have here, except exchanging the alpha with the beta, as I said. So we are going to look at how the microstructure development occurs at these different compositions and at these different intervals of the compositions, and we want to see that because it is important to understand what microstructure development are going to happen. To start with, we say from 0 to 2% by weight 10. For the lead 10 diagram, what is the microstructure which is going to develop? We cool down. Of course, the cooling down has to be done very slowly, lower than the diffusion process, in order to be able to predict the microstructure which is going to develop. That's a precondition on using the phase diagram, as we said right from the beginning. So if we cool down from here, if we are anywhere here above this temperature here, we are having only a liquid, because this area is all liquid. So we have liquid, and as we cool down, nothing is going to happen until we hit the liquidus line there. Once we hit the liquidus line, once we are just below the liquidus line, we are in this area. Which area is this? This is the two-phase region. We have the liquid and we have the alpha solid solution. So basically, since you have liquid already there, the alpha solid solution is the one which is going to develop. And it's going to develop in the material, and at different spots. It starts with the coolest place, and in different spots, the solid crystal is going to develop in randomly in different orientations, as we could see there, and it's going to increase up to that line until you reach the solidus line. This is called the solidus line. This is called the liquidus line. everything would have a transform. You just hit below that line, everything is going to transform. These are going to become bigger and bigger, and then they are going to transform into a polycrystalline because they have they develop in different orientations, so they become bigger and bigger until they impinge against each other with a mismatch between the grains, as we have seen previously, because of the different or random orientations of the atoms there, and you will be producing a polycrystalline alpha solid solution. And as you go down further and down, it will stay as it is up to 2% by weight 10. So you have a polycrystalline alpha solid solution which is going to develop. Very simple. Let's see, what do we have if we are differently? We are above 2%. We are in between 2% and nearly 18.3%, which is this point. What might develop? So, and this is what I'm saying, between 2% and 18.3% by weight net. So anywhere from here to here in terms of composition. If I come down here or come down from there or come down from here, of course we will have very similar microstructure with different compositions and amounts, but same microstructure we are talking generally. So if we were first of all in the liquid zone, here we have all liquid. This is the liquid area basically. So if we cool down, nothing is going to happen until we hit the liquidus line. Once we hit the liquidus line, we are cooling down further. The solid phase, the alpha, is going to develop in the material in different orientations. So and they are going to grow. So once they are formed, they are going to grow bigger and bigger and bigger and bigger until we hit the solidus line, sorry. And here everything turns into the alpha solid solution. In this area, you only have alpha solid solution. So basically, due to the different and random orientations of the atoms in each crystal, the crystals are going to nucleate in that way, and they are going to grow and impinge against each other again with a mismatch, and that due to that, the grain boundaries are going to develop. So you will develop a polycrystalline alpha solid solution there. From there, starting, and then as you cool down further and further, nothing is going to happen. You are in the alpha zone, basically. Nothing is going to happen until you reach the Salvus line there. This line, and at this line, basically, now if you are here. The solubility, if you remember the solubility, what's the solubility limit? It's the maximum amount. For example, the alpha solid solution is the mother material is 10, and is lead, and the 10 is the solute basically. So the lead can accommodate 10 up to that much, at that temperature up to that much, at this temperature up to that much. But as you reduce the temperature basically, as you could see, if you are here, for example, now the solubility limit of the 10 in lead reduced actually to this value. So the material here cannot accommodate the amount of 10 which is available in it. I mean, just going below that Salvus line, you see what was dissolved, what was accompanied, what was the amount of the 10 in the lead which was accommodated in this alpha solid solution is not anymore dissolvable in it. Let's say it's not anymore accommodated. Better to say that accommodated, because the solubility limit is less now. The solubility limit is this, while the amount of 10 that you have is much higher. So what is going to happen? And as you go further down, solubility actually decreases more and more, following that curve which we have. So the solubility limit at this here is that much. So this means that you have an amount of 10 in the material that as you are lowering the temperature there, you have an amount of 10 that cannot be accommodated. ما يقدرون يسكنونهم وياهم they cannot be accommodated in this alpha solid solution because the alpha has limited solubility الحين. Of course, solubility is reducing. What is going to happen if we have the amount of tin there more than the solubility limit of the 10 in the alpha phase? Another phase. Of course, if it was a liquid, then what is going to happen? It's going to precipitate at the bottom. But here, another phase is going to develop, and these are the needle-like phase beta, which is forming in randomly in different positions in the alpha solid solution there. So the other type, the other beta phase is going to develop, and as you can see in this zone, you have the alpha and beta developing. Why does the beta develop? Because the solubility limit actually reduces. So a dispersion, a random dispersion of the beta phase develops in the alpha phase there, and as you reduce further and further, more amount of beta is going to develop because the solubility is further decreasing and decreasing and decreasing, reaching to a minimum of 2% there. So you have more and more alpha developing in the material. So this is the final microstructure which develops at room temperature. It's a polycrystalline alpha solid solution with a precipitate, let's say, strengthening or random dispersion of the beta solid solution, needle-like solid solution dispersed in the material. So this is basically the microstructure we are going to get. Yes.
دكتور لما تقل السوليوبيليتي البيتا اللي بيزيد عدل؟
البيتا يتكون مو بيزيد.
يعني بيترسب عبارة.
البيتا هنا ما نقول يترسب، لأن لما تقول يترسب يعني شنو؟ يعني شنو يترسب؟
ليكويد يعني في ليكويد ويترسب.
أنا precipitation أو يترسب بالعربي يعني ينزل إلى مكان، هذه ما له إمكانية إنه ينزل، يتكون في السوليد، صح؟ يتكون نقول. it is going to develop. هني in here you don't have the beta. You don't have the beta phase here, do you? It's only alpha phase. There is no beta. There is 10 طبعا. The beta consists of 10 and lead. As you go down, the alpha phase cannot accommodate anymore the 10 as above here. شوف السوليبيليتي ماله أقل. فإنزين شو يسوي؟ البيتا اللي موجود sorry, and the alpha has a lot of 10. What does it do with the 10 then? It just goes and gathers them in different places. They 10 they gather in different places where they have high amount of 10, but of course there will be lead as well. So this is the other, and once they gather with high concentration of 10, it will be forming the beta phase, because the beta phase has high content of 10, high content of SM يعني. صح? This is what's going to happen. Any question?
دكتور؟
Yes.
يعني البيتا فيز ما بتتكون اول ما يعني يطلعوا من السوليدس لاين، يعني لازم يعني الكومبوزيشن تزيد بحد معين حتى تتكون البيتا فيز.
الكومبوزيشن مال الالوي ما قاعد يتغير. We are coming down with a constant composition which is the CO. صح؟
صح.
As we are coming down, yeah, composition is not changing for the alloy, but the alpha at that temperature has higher solubility. إنزين الحين خلينا نسهل الموضوع. افرض عندك جلاس شاي أو ماي، ترفع درجة الحرارة، السوليبيليتي ماله مثلا بيكون زايد، صح؟ It can dissolve a lot more sugar than lower temperature، صح؟ صح ولا لا؟
صح.
انزين as you lower the temperature شنو بيصير؟ solubility reduces. So إذا وايد في شكر super saturated, some of the sugar is going to precipitate. The same thing here. At higher temperature you have here higher solubility. Okay. It can dissolve 10 up to there. شوف ليه هالقد يقدر ياخذ، يقدر يدخله في بيته ضيوف ياخذهم ال 10 في الالفا. ليه هني up to there. But as you go down there, once you reach the Salvus line, now the solubility مالك هني. This is the line. This is the maximum solubility, but the amount which you have of 10 there is this much. So what happens? It needs to get rid of the 10. So what happens to the 10? They separate actually in different entities there with high concentration of 10 and develop the alpha phase, the beta phase. Clear?
دكتور لهذا
Clear.
السبب البرسنت كومبوزيشن ناخذ الفار سيجمنت لانه يمثل الديفلوبمنت مال الالوي الثاني. عدل؟
الحين أنا مو في ذي. I am talking about development of the microstructure. Okay, let that be on the side. وبعدين composition we don't take the far segment. هذاك when we are looking at the proportion, the weight fraction.
اقصد weight fraction.
Weight fraction you can say that, but we are now looking at microstructure. Okay, how it develops. Very logically, I'm very simply explaining it here. How this microstructure develops here. As you come down, the solubility reduces, the other phase beta is going to form. Very simple. Let's go to the next one. So we said from 0 to 2, and we explained from 2 to 18.3 how the microstructure will look like. Let's jump over this. We will come to it at the end. Let's go to the eutectic line and look at how the microstructure of the material develops. Then we are going to come back here and see how the microstructure here forms. So at the eutectic line, at the eutectic invariant point, what will be the microstructure? If you are above here at any temperature above 183 degrees centigrade, of course, since we are talking about eutectic point, we are looking at 61.9% by weight 10. So as we come down from there, we have basically a liquid. So that's the liquid that we are having in a green. As we go down, nothing is going to happen until we reach the eutectic point exactly. Once we are just below the eutectic point, what is going to happen? This microstructure is going to develop. This is called lamellar configuration. The lamellar configuration are lines, actually I could say it is alternating lines or layers of the two phases, because above that point you have only liquid, below that point you have two phases, you have the alpha and the beta, and they directly form after going just below the eutectic line. And it forms this lamellar configuration, which is the alternating layers of alpha, beta, alpha, beta, alpha, beta, like that in different colonies. In this colony, this is another colony here, and this is another colony. And in each colony, the orientations are different as well. So this is what we refer to as the eutectic microstructure. If you are at the eutectic composition, if you cool down, you get the lamellar configuration, which we refer to as the eutectic microstructure. And this is, we made it like that, but this is the real microstructure. As you could see, it looks like that. This is the alternating layers, basically, of the alpha and beta. This is one colony. This is another colony here. This is the third colony. This is the fourth one. So these we refer to as colonies there. And you have the alternating layers. Lamellar configuration of the alpha and beta. So that is the result of the microstructure that you are going to get. If you cool down here, you get this beautiful microstructure which you have here. Now just to think of how and why does this microstructure develop. Before we do that, we also want to look at, specifically for the tin lead, we already saw that the eutectic reaction equation here would be what? Would be going from liquid, if we want to write the eutectic equation, so which means that we will go from just above the eutectic point to just below the eutectic point here. So what's going to happen? What is that transformation equation? It's written here. I've already done that here for you. Above the eutectic isotherm, you have the liquid, and the liquid will be at 61.9% by weight 10. That is the point. At that point, that is the composition of the liquid. And just below the eutectic point, what phases do we get? We get the alpha and the beta, basically. And this is what we are having, alpha and beta. What is the composition of the alpha and beta which we are going to get? Okay. We will just below the eutectic isotherm, you draw a tie line. That's the tie line from here to there. It intersects here and it intersects there. So if we draw a vertical from there, you get 18.3. That is the composition of the alpha. That's the composition of the alpha which we are looking at. And if you intersect with a beta, you get the composition of beta. You drop a vertical from there, it is 97.8. And the beta phase has 97.8% by weight 10. And this happens at 183 degrees centigrade. So that's the full equation that we are having here. I'm not memorizing this equation. I have the phase diagram in front of me. I can say, if I have the phase diagram in front of me, I can clearly and very easily develop the equation there, which describes the eutectic isotherm transformation. Yes.
شنو نستخدم اليوتكتيك equation؟ يعني شنو نستفيد منها؟
نستفيد منها ان احنا يكون عندنا we are expressing the transformation as an equation. When we know how to determine these, we know how to develop also the quantities and the compositions of the different phases in the phase diagram. And we are going to come to this in a minute. Let's look at this. Yani what we did here. How did we solve this equations here? How did we find the compositions? Well, that's one practice that we need to do. The equation. This is normally how it is expressed. The point is expressed by a transformation. What is that transformation? It is expressed in this way. Okay, you need to know how the transformation happens. And instead of writing a full paragraph of what happens there, you write an equation to express that. This is another reason for why we do that. Majid Khan? Now, next, let me show why does this very strange and beautiful microstructure develop. يعني ليش when we go down from here it's a liquid, and when we just go down there this lamellar configuration develops in this way. Why is it that it is developing in this way or making this beautiful microstructure here, which we refer to as the eutectic microstructure? Well, let me explain it in this way. Again, relating to the solubility and the phases that we have here. If we are above that temperature, above the eutectic isotherm there, let me make this larger so that it is more clear. If we are above the eutectic isotherm, we are having a liquid. If we reduce the temperature from there to just below the eutectic isotherm, that's very fast. That's going very fast. We are just going across a point there from liquid to two solids, basically. So that is a very fast transformation the material needs to do. Going from one liquid phase into two solid phases. Not only that, notice from the composition of each phase, the alpha is at 18.3% by weight 10. The beta is at 97.8% 10. Not that we are going to two different solid phases directly, but also these two different solid phases have drastically different compositions as well. One is at 97.8 and one is at 18.3. So this means the material has to react very fast actually in order to do that. And the material, as you know, in terms of a solid, it does not have that much ability to do the transformation fast because of the diffusion process. But since you are going from liquid here, as it is liquid to solid, it might have some speed to do that, but it does not have enough speed to do much because, as I said, in order to go from a liquid with a homogeneous composition there into two different solids with drastically different compositions as we have determined there, it has to react very fast. So what does it do in order to do that? Let me explain to you in this way. For example, if you have the supervisor of the cleaners at the university, مثلا, he normally comes and jumps in and sees how the cleaners are working. Okay, that's a bad example, but I normally use it for to make it close to the students, actually easier for the students to understand. So what happens if the cleaners do not do their jobs as normal? So they play, they don't clean. All of a sudden, the supervisor shows up. So what happens there in the corridor? And what happens if the cleaners want to show that the corridors are clean? They just brush things to the side of the corridor, because the corridor is corners would not show the dirty sand or whatever there. So the supervisor normally notices the middle of the road, right? The middle of the corridor. So this is what they do. They push everything to the side, basically. So what does the material actually cheats in this way as well? Since it does not have time, and you have very little time for that transformation, the material does the same thing. The material, because it needs to develop two different phases with drastically different compositions there, so what it does there, in some segments or some layers of the material, it pushes the tin to the sides in order to make the rich lead area there, and the lead goes to that side and this side, and since the lead is here, the alpha is going to form here and the alpha is going to form here. The same thing with this area. It's going to push the tin to the sides, because that's much easier to do than developing a different microstructure. So it pushes the tin to the side here and there, and this becomes a lead-rich area, and it forms an alpha. The same thing here, and the same thing there, and so on and so forth. So this way, it will form this lamellar configuration, with which each layer becoming rich in a specific solid solution of these two. So in certain lamellae, you have a rich alpha rich tin, and you in tin, and in the next lamellae you have the beta solid solution, which is rich in tin, and so on and so forth. And this is how this lamellar configuration is developed in the material. Any question? No question. Now we will go to the last. Microstructure development. As we see here, we dealt with that point, and now we want to see what microstructure will develop as we go down from 18.3 to the eutectic composition there. As we go down here, or here, wherever, as we go down there, what microstructure is going to develop. So if we are here, we basically have liquid. As we go down further and further, as we hit the liquidus line there, the solid is going to form, because you have liquid and solid here. So the solid is going to form, and solid increases in amount as we go down, ruled by or manipulated by the tie line. If you draw a tie line there, for example, let me draw a tie line for you, since we don't have a tie line. So at the beginning, let's say the tie line is there. That's the tie line. And at the beginning, that's the alpha. At the beginning, alpha is that proportion divided by the total. So majority will be the liquid. And as you go down, that segment is basically increasing, and that segment is basically, you can notice that line coming down, and that segment is basically reducing. So the amount of you have the alpha solid solution forming in different orientation, and they are becoming bigger and bigger in amount as you reach up to just above the eutectic isotherm. So basically, you are going to get this phase. You have the alpha solid solution, and you have the liquid up to just above the eutectic isotherm. And that's the maximum amount of alpha which is going to form, this alpha which is going to form in the material. Once you go just below the eutectic isotherm, what is going to happen? The alpha phase is already formed in this shape. And normally we call this alpha as alpha prime here. Alpha prime because this alpha formed actually above the eutectic isotherm in this area. Once you come below the eutectic isotherm, what is going to happen? The alpha phase is already formed. It's a solid. It's not going to change. What is going to change is the liquid which we have here. The liquid is going to form the lamellar configuration because in the same way, that's the eutectic transformation, going from a liquid to two solid phases there. It does the same thing, and for the same reason, it forms the lamellar configuration, the alpha plus beta lamellar configuration, the alternating layers of alpha and beta. So basically, going from that point, just above the eutectic isotherm, to just below the eutectic isotherm, there is a fast transformation from the from the liquid to the alpha plus beta. The alpha which formed here, the primary alpha, will not change, and they will stay as they formed above the eutectic isotherm. This alpha is called the alpha prime, or it's called also the primary alpha. That other alpha which formed after the eutectic isotherm, it's called the secondary alpha. This alpha is called the secondary alpha, or sometimes this alpha prime is also referred to as pro-eutectic microstructure. And this is called, and that as well, of course, alpha and beta are called the eutectic microstructures, basically. So this is important to notice that when you are going from here to there, what is going to transform? The liquid is transforming into this lamellar configuration, and the alpha prime stays as it is in the microstructure of the material that you are having there. All right? Any question? If no questions, and this is what I want now. Next time, what we are going to do, I intended to do this here today. You remember at the beginning we did some exercise there. This exercise, we will learn that, well, not exactly, this is not how it is done. There is something else which we need to do, because when we are reducing the temperature to below the eutectic isotherm, it's not only two phases that we are looking at, alpha and beta, but we are also having the alpha prime here. And if we want to determine alpha prime and alpha and beta, well, there is a little bit different calculation that we need to do. Next time, we are going to do that and show how we will determine the alpha prime, the alpha, and the beta, all of them together. Okay? So we will stop here today, and we will continue with that. Any question?
دكتور باليوتكتيك بوينت كم فيز موجودة؟ 3 ولا 2؟
And this, when we cool down at the eutectic point?
ايه دكتور.
No, these are the two, alpha and beta, and all of them are called the eutectic microstructure. Beta eutectic, or you can say eutectic beta phase and eutectic alpha phase. Both of them, you are coming down across a point only. But here, if you cool down from there, no, there is an alpha which forms before you reach the eutectic isotherm, and that's why we called it alpha. The same thing here. If you are cooling down in this area and you are coming down there, you will have at the beginning formation of liquid plus beta. There is a primary beta phase which develops, and then when you reach just below the eutectic isotherm, you have alpha and beta forming again in the same way. All right? Let me stop the recording because